Hello to the Improve Your City Maintenance Using Machine Learning session. Greetings from Vilnius, Lithuania. My name is Gintaras Sakalas, and together with my colleague Kęstutis Daugęla, we are going through the session. The agenda today will be that we will talk about SEB as a company. We will talk about shortly about the event-driven architecture, how we built SEB PubSub streaming platform. Kęstutis will guide you through the Kafka log anomaly detection, anomaly management approach, and in the end, we will talk about the results and next steps. SEB is a leading Nordic financial service group founded in 1959 by Andrea Oskar Wallenberg. Since then, we've been guided by a strong belief that entrepreneurial minds and innovative companies are key in creating a better world. We are here to help them to achieve their aspirations and succeed them from the good times and bad times. We care for ambition. We naturally put our customers' needs first, always seeking to understand how to deliver real value. We are personally dedicated to the success of our customers and accountable for our actions. We strive to simplify what is complex. We achieve more working together. Our vision is to deliver world-class service and advice to our customers. SEB has global coverage with well-diversified business through different segments of industry. SEB is a number one in Nordic large corporates and institutions, Nordic payments, etc. 3,000 corporates and institutions, 400,000 small and medium enterprises, and more than 1.4 million private individuals are SEB clients. At SEB work 15,000 employees in more than 20 countries and more than 200 branch offices. 97% of all interactions with our clients are digital. That's all shortly about SEB, and let's talk about event-driven architecture. Event-driven architecture, or EDA, is a software architecture paradigm promoting the production, detection, consumption of, or reaction to events. An event can be defined as a significant change in state. For example, when a bank client closes the bank account state changes from open to closed. Architecture may treat this state change as an event whose occurrence can be made known to other applications within the architecture. What is published, produced, propagated, dedicated, or consumed is a message called the event notification, and not the event itself, which is state change that triggered the message emission. Events not travel, they just occur. Event-driven architecture gained a lot due to the need in innovation in enterprise system integration, especially when we're talking about ever-growing complexity. At SEB, we are using Kafka as a technology for this purpose, which is built as bulletproof with a high availability. Internally, we're naming this a PubSub or publish subscribe. Please do not mix it with other technologies which are named in a similar way. Kafka cluster running in multiple data centers with number of brokers and zookeepers. Data centers are physically located in different locations. Now let's talk about some stats. In our cluster, in total, we are running 18 Kafka brokers, 13 zookeepers, 21 Linux machines, and more than 10 different dashboards across the different environments. We do have more than 450 Kafka topics, and our production cluster is more than 85 terabytes. Okay, so what about the monitoring? This is the example of a couple dashboard showing different metrics and statistics. As you can imagine, the cluster is complex and difficult to take care of. It's really hard to track. It's limited intuition what's happening on a system level. So as we all IT guys, we're a little bit lazy. So we decided to employ machines and machine learning to take care of the cluster and to do our work so we can spend our time on more interesting things.
Hello, my name is Kęstutis and I will talk about our anomaly detection solution in more details. Our current setup is centered across system maintainers. There is no need to log into application and to the server directly and dig into the logs. We have a monitoring solution to do that for them. Issue is reported by various engines under the hood. We have static thresholds, rule-based filtering, forecasting servers, and ML-based log analysis. In case something serious happens, administrator informs related users and try to fix the issue as soon as possible. If it's not urgent, we just raise an incident and add to our backlog. It is really simple to monitor numeric variable. We just need to set static threshold, for example, for RAM usage or disk utilization. Forecasting is also a fairly easy problem for us, especially for hardware metrics. Normally, we use AutoRima or Phasos Profit algorithm for that purpose and do the retraining automatically. This approach actually saved us from many problems and helped us to ensure 24/7 runtime without any issues so far. It is really good to know when your server will be out of space, right? But what about anomalies? They are not presented in a convenient way, and since the data is unsupervised, it could be really tricky to identify bad or not usual system behavior. So first, let's define what is an anomaly. It is an item which differs dramatically from the majority of data. To put that definition in a simple words, it could be as simple as appearance of a red egg in a white eggs basket. But in our case, we are not counting eggs, we're having system logs, and we utilize unsupervised machine learning algorithms to do that for us. Our journey started with a simple approach, a Markov chain model. It was natural because each server generates a nice sequence of logs, so it perfectly fits this process. Of course, for modeling a Markov chain process, we need to draw some assumptions first, such as possible future states are fixed and probability of each event depends only on the state attained in previous event. In this case, we just need to invent feature which describes state. In Kafka server logs, we have at least two constant items, the log level and the Kafka server state, and this perfectly fits this feature. On the right side, you can see how we form a Markov chain. We are feeding the states to a model and it creates a graph of a probability matrix. So all we create is just the probabilities for the transition between one event and another. After that, we can identify anomaly depending on that probability. In green sequence, you can see that probabilities are high, so there are not anomalies here. But in the yellow sequence, you can see that some probabilities are not existing or is really low, so that indicates that these events might be an anomalies. But let's end our history lesson here and move on to more interesting models. This is because we needed more features and context in order to make our model more useful. Therefore, in addition to state, we also extracted associated topic, message time, and some additional keywords. After we generated these features, we feed them to autoencoder, which is trying to learn normal server behavior based on log data. Autoencoders are mostly popular for dimensionality reduction, feature extraction, image compression, but they can be used for anomaly detection as well. In addition to richer feature selection, enhanced sequence-to-sequence autoencoder model also grabs the context of the message. In our case, it's a window of 1000 messages around the current one. So for strong, we are feeding new data to autoencoder model, and depending on the reconstruction error for each log line, along with its context, of course, we put a dynamic filter in order to find anomalies. But the selection of features also seemed quite poor, taking into consideration all the additional data we have. Log contains a variety of different words, and we can also use log data in combination with other hardware metrics as well. Therefore, for our third model, we have decided to use Nlp Approach and word-to-vec algorithm. In addition to that, we have added time variable and binding hardware metrics such as CPU usage, RAM usage, disk utilization, and so on for each broker. So on the right side, you can see the graphical representation of such data in three-dimensional space. The size is representing the frequency of each log line, and the labels are the log level. Although errors are clustered nearby, there are lots of outliers and clusters worth for investigation. Once we had enough features, we have chosen isolation forest algorithm, a simple but yet elegant solution. This algorithm is really similar to the random forest, except for one thing. Instead of classification, it tries to isolate each point, and depending on the length of the tree, we can say whether it is an anomaly or not. This is fast and robust algorithm, so we can run it in distributed fashion, and also it works great in high dimensional space, as we have here. In order to visualize the outcome of these three anomaly detection models, we have created a separate dashboard for our TED guys. And by the way, we also have a fourth model, which is not actually a model, but it is a collection of simple rules and known list of anomalies, and it serves as a baseline model. So in this example, you can see what happens during the restart of one of the brokers, and this is pretty messy, I would say. But the good thing about this, that we can identify all the associated messages with that restart and do the root cause analysis afterwards, what caused the restart. And if it's not a restart, it could be any disturbance identified by this anomaly detection algorithm. Also, the ensemble approach helps us to have more complete view of the issue, and in case three completely different models agrees on that issue, then we can quite confidently say that the issue is anomaly. Eventually, we have incorporated anomaly management in our daily routine, and now it's everyone's responsibility to look into the anomalies and classify them. It also provided us greater visibility in terms of clients, existing topics, and what's happening in Graph cluster in general. Now, system maintainers don't need to log into each machine separately, but they can view the complete overview in one window. And we also democratize the access to the dashboard. So new developers can come in and see if their application caused any problems. As a side effect, we have some labels which we can use for rule-based filtering or supervised machine learning algorithms. On top of that, we have created a simple anomaly management application. And sorry for the interface, we have no user experience designers in our department. So this is what we come up with. Now administrators can either disregard the same message in the future or track them for later occurrence. Of course, we are retraining our models frequently using the new data, but in case of anomaly, it's better be safe than sorry and track them. This is how normal server behavior should look like from anomaly perspective overview. No anomalies found. But in addition to that, we have created a separate dashboards for each environment in order to preview some descriptive statistics, and it serves as just a sanity check. When it comes to our technology stack and pipeline, it's fairly simple. Firstly, we ship log text files to our monitoring hub. We don't use Kafka for that because it doesn't make sense to feed Kafka logs to Kafka. It will create an infinite loop of logging. We are parsing logs with both R and Python programming languages. TensorFlow is used for sequence-to-sequence autoencoder, and H2O framework is utilized for isolation forest Watt-Ver algorithm. Markov chain model is written in R. We also track our experiments and model version control via MLflow and use Jenkins for CI/CD pipeline. Later, we filter out the anomalies and write them to InfluxDB, which is a time series database. From there, it's fairly simple. It's just a couple of dashboards in Grafana wrapped in Shiny R application. That's all from my side, and now let's take a look what results we have accomplished when this anomaly management approach was implemented in SEB, and I'll give the stage to Gintaras.
Thank you, Kęstutis, for such detailed presentation. Let's go and talk about the results and the next steps. As a result of machine learning and implemented anomaly detection system, we managed to identify not authorized activities in the cluster. We managed to find issues with the software and raise tickets for the vendor. We identified not optimized applications which were caused by misbehaving producers or consumers. With developed anomaly detection system, we are able easily to manage alerts and enabling or disabling them. By having machine learning and maintenance process, we are able to do proactive support of the technologies we are using and improve provided services. Last but not least, with all of this, we increased our knowledge in more deep way. We did manage to achieve a lot. We do see this as a very good opportunity to extend monitoring capabilities and to have self-managed cluster by improving current and introducing new machine learning algorithms. Thank you for your attention, and I do hope that we managed to share our knowledge, and it was interesting for you. This is the core team which did this anomaly detection at SEB. Definitely, we managed this achieve with a much bigger team by cross-functional teams with our hardware network, and we delivered this in iterations as was presented by Kęstutis. We learned on the way, and in agile way, we managed to build this anomaly detection system. Thank you, and stay safe.